Chapter 2, we'll be talking about atoms and elements, and this is a quote from John Dalton. These observations have tacitly led to the conclusion, which seems universally adopted, that all bodies of sensible magnitude are constituted of a vast number of extremely small particles, or atoms, of matter. So, here's a thinking question. If you cut a piece of graphite from the tip of your pencil into smaller and smaller pieces, how far could you go? Could you divide it forever? Or would you get to a smallest piece that you couldn't cut? You don't have to answer that. Cutting that graphite into smaller and smaller pieces, we would end up with a piece that could not be cut in half, an individual carbon atom. The word atom comes from the Greek word atomos, which means indivisible. So you cannot divide a carbon atom into smaller pieces and still have carbon. Atoms are important because they compose all ordinary matter. I mentioned last week, I think of them as being little Lego bricks. And the entire universe is built out of atoms. So how did they come to understand that atoms actually existed? So in 1827, Robert Brown was looking at some water-suspended particles from pollen through a microscope. And he noticed that they were moving. So let's look at a video similar to what he would have seen. Stupid monetization. Particles that he was looking at. You see how they're wiggling? Why? What's going on there? So what's causing the motion? Initially he thought it might be living organisms, right? Because they look like they're alive. Right? But
good afternoon, this is Mr. McGee. A common question I get asked by my students is, how do we know that atoms are real? Well, rather than just sit there and tell them stuff, I'd rather them see with their own eyes. And I want to show you that same evidence that a Swedish botanist named Robert Brown first saw.
Okay, so I'm sure that video would be very, very interesting, but we're not watching that video. Whoops, now we're all messed up. So he finally concluded that the motion, the source of the motion, was not from the particles themselves, it was from something outside the particles. In 1905, Albert Einstein came up with a theory that explained Brownian motion. So Brownian motion was an observation, but it didn't explain anything. And so Albert Einstein's theory is explaining it, and his explanation that water molecules in the liquid are moving, and they're battering those pollen and dust particles, causing them to vibrate. So if you imagine a big crowd of people and you throw some beach balls in there, and people are hitting them or they're just bouncing off of the unobservant people's heads, and if you just looked at the beach balls, they'd just be kind of making this random motion and not necessarily traveling, but just kind of wiggling around. So that's what's happening to these particles. The particles are large enough that we can see them with a microscope, but we can't see the water molecules. But the water molecules are hitting them. So the Brownian motion infers, but does not prove, the existence of atoms. But Jean Perrin did some measurements later that confirmed Einstein's theory. And then there was no doubt that atoms are real. Now, in the 1980s, a very cool technique was developed at IBM called scanning tunneling microscopy, abbreviated STM. So this is a huge device. We're only looking at a little tiny part of it. So there's this probe, and at the probe is a very sharp needle. And at the very end of that is a single atom. And so what they're doing is they're applying a voltage and sending a tunneling current through the air from the tip of this needle to the surface of the thing being examined. So the magnitude of that current is going to depend on how far apart these two things are. And so by monitoring this and moving the needle up and down in a way to make the constant current, as you go back and forth across the thing you're looking at, essentially you're feeling the surface. There's nothing optical about this. We take the signals we get from the computer and we can make it into an image, but it's not a microscope in the sense that you're just magnifying vision. So that's kind of my rough explanation. And let's watch this movie. It's a different, slightly different.
So what we do to move atoms is a variation of what we do to see the atoms in the first place. So we can't use light to see them. So we're not looking through a microscope like the conventional microscope we're used to. We need something that can see much smaller things than that. So what we do is take a sharp metal needle and bring it close to the atoms. And in a sense, we're feeling the shape of the atoms. So if you imagine that we have a surface that we're putting an atom on, we put it on the surface and so it holds still. What we do is take this metal needle close to the atom and sense its presence by measuring an electric current that flows. And as the tip of this needle approaches the atom, it sees more electric current, and we draw it up and over the atom to keep that current constant. So in a sense, we're feeling the shape of this atom. Then in order to move atoms, we observe that we have a sharp metal needle near it. We can bump into it by accident. What we can do is, instead of doing it by accident, do it under control. If this is our atom on a surface, we can move the tip close and we start to form a chemical bond between the tip and the atom. That chemical bond forms between most atoms. They like to bond to each other in most cases. So we start to form a bond such that the atom follows the tip around on the surface. We can drag it to a new spot. When we withdraw the tip, it holds still because the surface is holding it in place. And we can take an image and see where we've placed this atom. So that process, repeated over and over, is how we've built most of the structures in our lab. That's our bread and butter basic technique for moving atoms around.
So IBM uses that to make extremely small circuit boards, right? So you can make a wire that's like just 2 or 3 atoms wide, right? So then everything can become much, much smaller. So this is a picture made using that technique of moving the atoms. So they've taken some iron atoms, those are the ones that are kind of reddish purple here, on a copper surface, and they've arranged them in the shape of the Japanese kanji characters for atom. And then, you can have more fun with moving atoms around. IBM also made the world's smallest movie, A Boy and His Atom. I'm receiving no compensation from IBM. So this is stop motion animation. Anybody have any questions? It's not going to win any Emmys.
I like how the first thing we do when we learn how to move atoms is make a
Yeah, the first thing we do, we learn how to move atoms, and we make a silly movie about a ball, bouncing around. Or we write things with the atoms, right? So I think scientists may have a reputation of being stuffy and boring, but actually we have deranged senses of humor. And so, yeah, we do stuff like this. So I just want you to have some grasp of how small atoms are. So the Library of Congress contains 35 million books on 870 miles of shelving. So imagine a bookshelf, 840 miles long. If you took all the words in all of those books and wrote them using atoms the size of those kanji characters, all the words would fit in an area of 5 square millimeters. It's really, really, really tiny. And yet, in spite of their incredibly small size, atoms are the key for connecting between the macroscopic world and microscopic or particulate world. So the atom is the smallest identifiable unit of an element. There are 91 different naturally occurring elements and over 20 synthetic elements. Those that are not found in nature, they're made by humans. They're not stable, and so, you can make them, and then they fall apart. That's why they don't exist in nature, because they're not stable. And so these guys down here that are just have their initials or their symbols outlined, those are all man-made elements. And why do people make new elements? Just to see if they can.